Welcome to Sleepy Cosmos Stories. I'm so glad you're here tonight. Before we begin, take a moment. Where are you right now? Are you in a quiet bedroom, nestled under soft blankets? Perhaps you're in a comfortable chair, the day finally winding down. Or maybe you're somewhere else entirely, just seeking a moment of peace. Wherever you are, I hope you're comfortable, safe, and ready to let your thoughts gently drift. If you enjoy these calming cosmic journeys and would like to hear more, a like or subscribe really helps this small channel continue. And to those already subscribed, thank you. Your support means more than you know. Tonight, we're exploring one of the universe's most fundamental truths, a truth so obvious that we rarely notice it, yet so profound that it shapes everything we know. Nothing in the universe stands still. Not you, not Earth, not the Sun, not even the galaxies themselves. Everything is moving, spinning, orbiting, drifting, and it has been since the very beginning. Tonight, we'll discover why. We'll explore the cosmic dance that began 13.8 billion years ago and continues to this very moment. We'll understand why stillness is impossible, why motion is written into the very fabric of existence. I promise not to make this too interesting, just interesting enough. Enough to occupy your mind without keeping it awake. Enough to remind you that you're part of something vast, beautiful, and remarkably graceful. So, shall we begin? Take a deep breath, and let's step into the universe's eternal dance together. Let's go back, all the way back, 13.8 billion years ago. Before there were stars, before there were atoms, before there was space as we know it. Everything that exists, every particle, every bit of energy, every possibility was compressed into an infinitesimally small point. And then it exploded. Not into space. Space itself was created in that explosion, the Big Bang. In that first fraction of a second, far less than a blink of an eye, the universe expanded, faster than light, faster than anything we can truly comprehend. And in that expansion, something remarkable happened. Motion was born. Not just expansion, but rotation, spin, angular momentum. Why? Scientists believe it came from quantum fluctuations, tiny random variations in the fabric of space-time itself. These fluctuations weren't perfectly symmetrical. Some regions had slightly more energy, some slightly less. And as the universe expanded, these tiny imbalances created motion. A slight push here, a gentle tug there. And once that motion started, it never stopped. Because in the vacuum of space, there's nothing to slow it down. No friction, no air resistance, no force opposing the motion. So everything that started spinning 13.8 billion years ago is still spinning today. The galaxies, the stars, the planets, even the particles inside atoms, all of them carrying the momentum from that first moment. The universe's original dance, still continuing, still graceful, still relentless. And you're part of that dance too. Right now, as you read these words, you're moving through space at incredible speeds, not because you chose to, but because the universe, at its birth, set everything in motion, and nothing has stopped since.
What is angular momentum, the universe's most stubborn property? Before we go further, let's talk about angular momentum. It sounds complicated, but it's actually quite simple. Angular momentum is the property of rotating objects. It's what keeps them spinning. And here's the key. Angular momentum is conserved. What does that mean? It means that once something starts spinning, it will keep spinning unless an external force acts on it. Think of a figure skater. When they spin with their arms extended, they rotate slowly. But when they pull their arms in close to their body, they spin faster. Why? Because their angular momentum must be conserved. Same total spin, but concentrated in a smaller space, so the rotation speeds up. The universe works the same way. When a cloud of gas and dust in space starts to collapse under gravity, it spins faster and faster, because as it shrinks, its angular momentum is conserved, concentrated, amplified. This is how stars form, how planets form, how galaxies form. They all spin because the original cloud they came from was spinning. And that original spin, it came from the Big Bang. From those first quantum fluctuations, from the first moments of existence. Angular momentum is the universe's memory, a record of the very beginning, written into the rotation of everything that exists. And because it's conserved, it never goes away. A spinning galaxy will spin for billions of years, trillions. A rotating planet will keep rotating, slowly, perhaps, losing a bit of speed to tidal forces, but never stopping completely. Not unless something dramatic happens, a massive collision, an external force. But even then, the angular momentum doesn't disappear. It just transfers, changes form, like a cosmic dance where partners change, but the music never stops. Angular momentum is stubborn, persistent, eternal. And it's why nothing in the universe can truly stand still. The first spin, when particles began to rotate. In the first moments after the Big Bang, the universe was a seething soup of particles. Quarks, gluons, photons, energy in its purest form. Too hot for atoms to exist, too chaotic for structure. But even in that chaos, there was motion. Particles zipping around at near light speed, colliding, transforming, dancing. And many of them were already spinning. Not spinning like a top, but spinning in a quantum sense. Particles have a property called spin. It's one of their fundamental characteristics. Electrons have spin, quarks have spin, even photons, particles of light, have spin. But here's the strange thing. This spin isn't anything we experience in the everyday world. An electron isn't actually rotating. It's not a tiny ball spinning on an axis. Its spin is intrinsic, a fundamental property, like mass or charge. And yet it behaves mathematically like angular momentum. It's conserved, it can be transferred, it creates measurable effects. Quantum spin is one of the universe's deepest mysteries. We can measure it, calculate it, predict it, but we don't fully understand what it really is. All we know is this: from the very beginning, particles had spin, and that spin has been with them ever since. Every electron in your body, every quark in every atom, they're all spinning, in their strange quantum way, carrying momentum from the first moments of the universe. It's as if the Big Bang set everything spinning, and nothing has stopped. Not the galaxies, not the stars, not even the tiniest particles. Everything is in motion. Everything is dancing. And it has been for 13.8 billion years.
Why didn't everything just explode outward in straight lines? Here's a question you might be wondering. If the Big Bang was an explosion, why didn't everything just fly apart in straight lines? Why did things start rotating, orbiting, spinning? The answer lies in those quantum fluctuations we mentioned earlier. The Big Bang wasn't perfectly symmetrical. It wasn't a neat, orderly explosion. It was messy, chaotic, full of tiny variations. Some regions had slightly more energy, some slightly less. Some regions expanded slightly faster, others slightly slower. And as these regions interacted, they didn't just push away from each other in straight lines. They tugged, they pulled, they curved each other's paths. Gravity was already at work, even in those first fractions of a second. And gravity doesn't create straight-line motion. It creates curves, orbits, spirals. When two objects pass near each other in space, gravity bends their paths. If they're moving fast enough, they curve around each other and fly apart. If they're moving at just the right speed, they orbit. And if they're moving too slowly, they collide and merge. In the early universe, all three things happened constantly. Particles collided, merged, formed larger structures. And as they did, they inherited the angular momentum of the particles that formed them. A cloud of gas formed from billions of particles, each with their own motion, their own spin. The net result? The cloud itself rotates. And when that cloud collapses to form a star or a galaxy, it spins even faster because angular momentum is conserved. This is why galaxies are spiral-shaped, why planets orbit stars, why moons orbit planets. It's all because the universe wasn't born still. It was born moving, spinning, dancing, and it never stopped.
The cosmic speed you're traveling right now. Let's bring this down to Earth, literally. Right now, you're moving, fast. You might feel like you're sitting still, lying still, completely motionless, but you're not. First, Earth is rotating, spinning on its axis. At the equator, that means you're moving at about 1,670 kilometers per hour, over 1,000 miles per hour. If you're farther from the equator, it's a bit slower, but still fast. You don't feel it because everything around you is moving at the same speed, the air, the ground, everything. But you're spinning right now. One complete rotation every 24 hours, every single day of your life. And Earth doesn't just spin, it orbits the sun at about 107,000 kilometers per hour. That's nearly 30 kilometers every second, faster than any vehicle humans have ever built. You're hurtling through space right now as you read this. But it doesn't stop there. The sun itself is moving, orbiting the center of the Milky Way galaxy at about 828,000 kilometers per hour. It takes the sun about 225 million years to complete one orbit around the galaxy. The last time we were at this exact point in our galactic orbit, dinosaurs were just beginning to appear on Earth. And the Milky Way? It's moving too. It's falling toward the Andromeda galaxy at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide, merge, form a new, larger galaxy. But even that's not the end. The entire local group of galaxies, our cosmic neighborhood, is moving, pulled by the gravity of an enormous supercluster called Laniakea. We're drifting through space toward the Great Attractor at over 600 kilometers per second. Add it all up, and you're moving through space at speeds that would make your head spin. But you don't feel any of it, because motion in space is smooth, constant, graceful. There's no jolt, no acceleration, just a steady glide. You're part of the universe's dance, whether you know it or not, spinning, orbiting, drifting, never still, never stopping. And that's okay, because stillness in the universe doesn't exist. Why stopping is impossible. Here's a thought experiment. Imagine you wanted to stop completely. Not just stop moving relative to Earth, but stop moving relative to the universe. To find a point in space where you're absolutely perfectly still. Could you? No. And here's why. First, there's no such thing as absolute space. no fixed reference point. Einstein taught us this. Space and time are relative. You can only measure motion relative to something else. You might be still relative to Earth, but Earth is moving relative to the Sun. You might stop relative to the Sun, but the Sun is moving relative to the galaxy. You might stop relative to the galaxy, but the galaxy is moving relative to other galaxies. There's no universal still, no absolute zero of motion. Every frame of reference is moving relative to something else. So stopping is meaningless. You can only stop relative to one thing, but you'll still be moving relative to everything else. But let's say you tried anyway. You fired rockets, adjusted your course, tried to cancel out all motion. What would happen? You'd immediately start moving again, because gravity is everywhere. Every mass in the universe pulls on every other mass. Even if you somehow managed to cancel out all your motion, gravity would immediately start pulling you towards something. The nearest star, the nearest galaxy, the nearest anything, and you'd start moving, accelerating, falling. Motion would return instantly. You can't escape it. Motion is the default state of the universe. Stillness is the illusion. And it's been that way since the Big Bang. When the universe was born, it was born moving, and it will keep moving forever.
The atom, a universe of motion. Picture an atom. You've probably seen the classic image, a nucleus at the center, with electrons orbiting around it like planets around a sun. It's a neat picture, simple, easy to understand. But it's not quite right. Electrons don't orbit like planets. They don't follow neat circular paths. Instead, they exist in probability clouds, regions where they're likely to be found. But here's the key. They're always moving. Electrons never sit still. They can't. It's not just that they choose to move. It's that stillness for an electron is impossible. Why? Because of something called the Heisenberg uncertainty principle. This principle says that you can never know both an electron's exact position and its exact momentum at the same time. The more precisely you know where it is, the less you know about how fast it's moving. And the more precisely you know its speed, the less you know about its location. But here's the thing. If an electron were completely still, zero momentum, you would know its momentum exactly, zero. And according to the uncertainty principle, that would mean its position would be completely unknown. It could be anywhere in the universe. That doesn't make sense. So electrons can never be still. They must always have some motion, some momentum. It's built into the quantum rules that govern the universe. Electrons are always moving, buzzing around the nucleus, not in neat orbits, but in constant, restless motion. And that motion creates energy. Even at absolute zero, the coldest possible temperature, atoms still have motion. It's called zero-point energy, the minimum energy that quantum systems possess. Even when you remove all the heat, all the thermal energy, the quantum motion remains. Particles jitter, vibrate, move, because stillness is forbidden by the laws of physics. Your body is made of atoms, trillions of them, and every single one is in constant motion. Right now, as you rest, as you breathe. The atoms in your skin, in your bones, in your brain, all of them moving, vibrating, never still. You are not a solid, static object. You are a dynamic, ever-moving collection of particles. A dance of atoms, held together by forces, shaped by motion. And that dance never stops.
Temperature is just motion in disguise. Let's talk about heat. What is heat, really? It feels like a thing, a quality, something that flows from hot objects to cold ones. But at the atomic level, heat is just motion. When something is hot, its atoms are moving fast, vibrating intensely. When something is cold, its atoms are moving slowly. Temperature is just the average kinetic energy of particles. The faster they move, the hotter the object. The slower they move, the colder. But they're always moving. Even ice, even frozen solid. The atoms in ice are vibrating. Locked in place, yes, but still vibrating, still moving. If you could zoom in and watch, you'd see them jittering, shaking, like people standing in place, shivering from the cold. And as you add heat, as you warm the ice, the vibrations get stronger, faster. The atoms shake more violently, until finally they shake so much that they break free of their positions. The solid becomes liquid. Ice melts into water. And in liquid water, the atoms are moving even more, sliding past each other, flowing. Heated further, and the motion becomes even more intense. The atoms move so fast that they break free entirely. Water becomes steam, a gas, molecules flying apart at high speed. But even in steam, the motion isn't random. It's chaotic, yes, but it follows rules. The laws of thermodynamics, the conservation of energy, the principles of motion. Everything is connected. Everything is in motion. And that motion is what we perceive as heat. So when you feel warmth on your skin, you're feeling motion. Atoms in the air or in the sunlight, transferring their motion to the atoms in your skin, making them vibrate faster, making them warmer. Heat is motion. Temperature is motion. And at the atomic level, motion never stops. Even in the depths of space, where the temperature is just a few degrees above absolute zero, atoms still move. Slowly, gently, but always. Because absolute stillness is impossible. The universe won't allow it.
In 1827, a botanist named Robert Brown was looking at pollen grains suspended in water. Under his microscope, he noticed something strange. The pollen grains were moving, jittering around, randomly, not in straight lines, not in any predictable pattern, just wiggling. He thought maybe the pollen was alive, that's why it was moving. But then he tried it with dust particles, with tiny fragments of glass, with anything small enough to float in water, and they all moved the same way. Random, jittery, restless. What was causing this? It took decades to figure out, but eventually scientists realized the particles were being hit by water molecules. Water, even at room temperature, is full of motion. The molecules are constantly moving, vibrating, colliding. And when billions of them hit a pollen grain from different directions, the grain moves, pushed one way, then another, constantly buffeted by invisible impacts. This is called Brownian motion, and it's direct evidence that atoms and molecules are always moving. You can see it yourself with a decent microscope and a drop of water. Tiny particles dancing, jittering, never still, because the water molecules around them never stop moving. Brownian motion happens everywhere. Dust particles in the air are doing it right now, floating, drifting, pushed by collisions with air molecules. Particles in your blood are doing it. Red blood cells suspended in plasma are constantly being jostled by water molecules. Even the molecules of your DNA, inside the nucleus of your cells, they're vibrating, flexing, moving. Nothing is still, not even inside the most stable solid structures in your body. Everything is in motion, constant, eternal. And Brownian motion is the proof, visible evidence of the invisible dance. Let's zoom out slightly from atoms to molecules.
A molecule is a group of atoms bonded together. Water, for example, H2O, 2 hydrogen atoms and 1 oxygen atom. But even when atoms bond, they don't lock into place. The bonds themselves vibrate. Imagine 2 atoms connected by a spring. The spring stretches and compresses back and forth, constantly. That's what chemical bonds do. They vibrate. In a water molecule, the bonds between hydrogen and oxygen are vibrating thousands of times per second, trillions of times. The atoms are also rotating, spinning around each other, and the molecule as a whole is moving, translating through space. So every molecule has 3 types of motion: vibrational motion, the bonds stretching and compressing; rotational motion, the molecule spinning; and translational motion, the molecule moving through space. All 3 happening simultaneously, constantly. And this is true for every molecule in existence. The air you're breathing right now, full of nitrogen and oxygen molecules, all of them moving, vibrating, spinning. The water in your body. Every H2O molecule is in constant motion. The proteins in your cells, they're not static structures, they're dynamic, flexing, vibrating, changing shape constantly. Life depends on this motion. Enzymes, proteins that catalyze chemical reactions, only work because they're moving. They flex, they change shape, they grab onto other molecules, twist them, and release them. If they were still, they wouldn't work. Life would stop. Your DNA is the same. It's not a static ladder. It's a dynamic, writhing, twisting structure. The double helix rotates, unwinds, rewinds constantly, because the molecules that make it up are in constant motion, vibrating, spinning, never resting. You are not a solid, unchanging thing. You are a dynamic process, a dance of molecules, and that dance is what keeps you alive.
How fast are molecules moving? It depends on temperature, but at room temperature, in the air around you, molecules are flying. Nitrogen molecules, the most common in air, are moving at about 500 meters per second. That's over 1,800 kilometers per hour, faster than the speed of sound. Oxygen molecules are moving at similar speeds. These molecules are zipping around you right now, colliding with each other billions of times per second. Each collision changes their direction, sends them flying in a new path. It's chaos, complete random chaos. And yet, from that chaos, order emerges. Air pressure, temperature, sound, all of it arises from the collective motion of countless molecules. Inside your body, molecules are moving too, but in a liquid like blood or cellular fluid, they move more slowly, maybe a few hundred meters per second instead of 1,000. But they're still fast, still constantly in motion, and they have to be, because your body depends on that motion. Oxygen molecules need to move from your lungs to your blood. Nutrients need to diffuse through cell membranes. Waste products need to be carried away. All of this happens because molecules are in constant random motion. Diffusion, the process by which molecules spread out from areas of high concentration to low concentration, it's driven entirely by molecular motion. If molecules stopped moving, diffusion would stop, and you would die. Your cells would run out of oxygen, fill with waste, cease to function. Motion is life, and at the molecular level, motion never stops. Here's something truly strange. At the quantum level, particles don't just move through space, they can move through barriers. It's called quantum tunneling. Imagine a ball rolling toward a hill. If it doesn't have enough energy, it rolls back down. It can't go over the hill. That's classical physics. Makes sense. But in quantum physics, particles can sometimes pass through the hill, even if they don't have enough energy to go over it. They tunnel through.
How? It has to do with the wave-like nature of particles. At the quantum level, particles aren't just particles, they're also waves. And waves can extend beyond barriers, leak through, exist on the other side. Most of the time, the particle stays on one side, but occasionally, randomly, it appears on the other side. It tunneled through. This isn't science fiction, it's real, and it happens constantly, in your body, right now. Nuclear fusion in the sun depends on quantum tunneling. Protons in the sun's core don't have enough energy to overcome the electromagnetic repulsion between them, but they tunnel through, fuse together, release energy. That's where sunlight comes from, quantum tunneling. And it's happening in you too. Enzymes use quantum tunneling to transfer electrons. Some researchers believe quantum tunneling plays a role in how our sense of smell works. Particles don't just move through space, they move through impossible barriers. Because at the quantum level, the rules are different. Nothing is truly solid, nothing is truly still. Everything is fluid, probabilistic, in motion. And that motion includes tunneling through walls.
Your body, a symphony of motion. Let's bring this back to you. Right now, as you read these words, your body is a symphony of motion. Your heart is beating, muscle cells contracting and relaxing about 60 to 100 times per minute. Your lungs are expanding and contracting, air molecules rushing in and out. Your blood is flowing, cells tumbling through vessels, oxygen molecules diffusing across membranes. Your neurons are firing, electrical signals racing along nerve fibers, neurotransmitters crossing synapses. Your cells are dividing, DNA unzipping, proteins being assembled, molecules being transported. Every process in your body depends on motion. And all of that motion ultimately comes down to atoms and molecules, moving, vibrating, spinning, colliding, never still, never resting. You are not a thing, you are a process, a dynamic, ever-changing dance of matter and energy. And that dance is what makes you alive. If the atoms in your body stopped moving, you would die, instantly. Your cells would freeze, chemical reactions would halt, neurons would stop firing. Life is motion. And motion, at the atomic level, never stops. Even in death, atoms continue to move. They disperse, join other molecules, become part of the soil, part of plants, part of other living things. The motion continues. The dance goes on, just in different forms. You are made of atoms that were once part of stars, that were once part of ancient oceans, that were once part of dinosaurs, perhaps. And when you're gone, those atoms will continue, moving, dancing, becoming part of something else. The universe doesn't let anything rest. Not in life, not in death. Motion is eternal.
Let's start with the most familiar spinning object, Earth. Right now, you're on a planet that's rotating, spinning on its axis once every 24 hours. But why? Why does Earth spin? And why hasn't it stopped? The answer takes us back 4.6 billion years to when Earth was forming. Our solar system began as a vast cloud of gas and dust, drifting through space, slowly collapsing under its own gravity. But this cloud wasn't perfectly still. It had motion, rotation. Maybe from the turbulence of nearby supernovae, maybe from the overall rotation of our galaxy, maybe from random eddies in the interstellar medium. Whatever the cause, the cloud was spinning, slowly, gently, but definitely rotating. And as it collapsed, something remarkable happened. Remember angular momentum? the property that keeps spinning things spinning? As the cloud contracted, it spun faster, just like a figure skater pulling in their arms. The cloud flattened into a disk, a spinning disk of gas and dust with the infant sun forming at the center. And within that disk, particles collided, stuck together, gradually built up larger and larger objects. Dust grains became pebbles, pebbles became boulders, boulders became planetesimals, planetesimals became planets. And every collision added angular momentum. When two objects hit each other at an angle, not head-on but glancing, they start spinning. Earth formed from thousands, millions of these collisions, each one adding a little spin, a little rotation. And the net result? A planet spinning on its axis. Earth inherited its rotation from the cloud that formed it, from the countless collisions that built it. And once it started spinning, it never stopped. Because in the vacuum of space, there's no friction to slow it down, no air drag, no resistance. Earth has been spinning for 4.6 billion years, and it will continue spinning for billions more. That's why you have day and night, why the sun rises and sets. Not because the sun is moving around Earth, though it looks that way from our perspective, but because Earth is spinning, rotating beneath the sun's steady light. One rotation every 24 hours, every single day of your life, and every single day since Earth formed. It's a memory, a record of birth, written into the planet's motion, and it will continue, patiently, reliably, forever. But Earth's spin isn't entirely constant. It's slowing down, very, very slowly. Every century, Earth's rotation slows by about 1.7 milliseconds. That doesn't sound like much, and in a human lifetime, it's unnoticeable. But over geologic time, it adds up. 600 million years ago, a day on Earth was only about 21 hours long. 2 billion years ago, maybe 18 hours. When Earth first formed, a day might have been just 6 hours. Earth has been slowing down for its entire existence. Why? The moon. The moon's gravity pulls on Earth. Specifically, it pulls on Earth's oceans, creating tides. High tide, low tide, twice a day. But Earth is spinning faster than the moon orbits, so the tidal bulges, the high tide regions, are dragged ahead of the moon by Earth's rotation. And those bulges pull back on the moon, gravitationally. It's a subtle effect, but it's real. The result? Earth's rotation slows down, and the moon drifts away, about 3.8 centimeters per year, slowly, patiently. One day, far in the future, billions of years from now, Earth's rotation will slow so much that one side will always face the moon, just like the moon already does with Earth. Tidal locking, a state of balance where rotation and orbit synchronize. But that won't happen for a very long time, long after the sun has died. For now, Earth continues spinning, slowing, yes, but still fast enough that you have a 24-hour day. And even when it does slow further, it won't stop. It will just reach a new equilibrium, a new rhythm. Because stopping isn't an option. The universe doesn't allow stillness.
Now let's talk about orbits. Earth doesn't just spin, it also orbits the sun, once every 365.25 days, a year. But why does it orbit? Why doesn't it just fly off into space or fall into the sun? The answer is beautiful in its simplicity. Earth is falling toward the sun right now, constantly, but it's also moving sideways, fast, about 30 kilometers per second, over 100,000 kilometers per hour. And because it's moving sideways so quickly, it keeps missing the sun. It falls toward the sun, but the sun curves away beneath it. So Earth falls and falls and falls, in a curved path, forever. That curved path
is an orbit. Orbiting is just falling with enough sideways motion that you never hit the ground. The International Space Station does the same thing. It's falling toward Earth, constantly, but it's moving sideways at about 28,000 kilometers per hour, so it keeps missing Earth. It falls around the planet, over and over. That's what an orbit is. Earth is doing the same thing around the Sun, falling, forever, in a graceful elliptical path. And this motion comes from the same place as Earth's spin, from the rotating disk of gas and dust that formed the solar system. Particles in that disk were already moving in circular paths around the infant Sun. As they clumped together to form planets, they kept that orbital motion. Earth inherited its orbit from the cloud that birthed it. And just like its spin, the orbit is stable, enduring. There's no friction in space to slow it down, no air drag. So, Earth will continue orbiting for billions of years, until the Sun expands into a red giant and swallows it, or until some massive gravitational disturbance, extremely unlikely, knocks it out of orbit. But barring catastrophe, Earth's orbit is eternal, a dance that began 4.6 billion years ago and will continue for billions more. Graceful, patient, relentless. Earth isn't unique. Every planet in the solar system spins. Mercury spins, slowly, once every 59 Earth days. Venus spins even more slowly and backward, once every 243 Earth days. Mars spins at almost the same rate as Earth. A Martian day is just 37 minutes longer than an Earth day. Jupiter, the giant, spins fastest. Despite being over 300 times more massive than Earth, it completes a rotation in less than 10 hours. Saturn, Uranus, Neptune, all spinning, each with their own rate. Why do they all spin? For the same reason Earth does. They formed from a rotating disk of gas and dust. They inherited angular momentum from countless collisions, and once they started spinning, they never stopped. But here's the interesting thing. They don't all spin in the same direction. Most planets spin in the same direction as they orbit, counterclockwise when viewed from above the Sun's north pole. But Venus spins backward, clockwise, and Uranus spins on its side. Its axis is tilted 98 degrees. It's basically rolling around the Sun like a ball. What happened? Collisions, massive ones. Early in the solar system's history, planets and planetesimals were still crashing into each other. A huge impact could knock a planet's spin off kilter. Venus was probably hit by something massive, flipping its rotation. Uranus likely suffered a collision so violent it knocked the entire planet onto its side. But even these dramatic events didn't stop the motion. The planets still spin, just in different directions, at different angles. Because angular momentum is conserved. It can change direction, but it doesn't disappear. The solar system is a collection of spinning worlds, each with its own history, its own story, but all of them sharing the same fundamental truth. They spin because they were born spinning, and they will keep spinning until something stops them, which, in the emptiness of space, is unlikely to ever happen.
Look up at the moon tonight. If it's visible, you'll see familiar features: the dark patches, Maria, ancient lava plains, the bright highlands. And here's something remarkable: those features never change position. The moon always shows us the same face. The near side is all we ever see from Earth. The far side, often incorrectly called the dark side, is forever hidden from our view. Why? Because the moon is tidally locked to Earth. It rotates once on its axis in exactly the same time it takes to orbit Earth once, about 27.3 days. So as the moon orbits, it rotates at exactly the same rate, keeping one face toward Earth. Imagine walking in a circle around a chair, always facing the chair. You'd be rotating, turning, but from the chair's perspective, it would look like you're not rotating at all. That's what the moon is doing.
But this isn't a coincidence. It's the result of tidal forces. Billions of years ago, the moon rotated faster. It had its own day-night cycle, independent of its orbit. But Earth's gravity pulled on the moon, creating tidal bulges. Those bulges acted like a brake, slowing the moon's rotation. Over millions of years, the moon slowed down and slowed down until its rotation matched its orbit. At that point, the tidal bulges aligned. The braking stopped. The system reached equilibrium. Tidal locking. And now the moon is locked, forever showing the same face to Earth. Most moons in the solar system are tidally locked to their planets. Io, Europa, Ganymede, Callisto, Jupiter's largest moons, all tidally locked. Titan, Saturn's giant moon, tidally locked. Even Pluto and its moon Charon are mutually tidally locked. They always show the same faces to each other. It's a natural end state, a gravitational embrace, and it's another form of motion. The moon is still spinning, just synchronized with its orbit. A perfect dance, a cosmic waltz, where two bodies move as one. Earth isn't spinning straight up and down. Its axis, the imaginary line through the north and south poles, is tilted by about 23.5 degrees, and this tilt is why we have seasons. When the northern hemisphere is tilted toward the sun, it's summer there, more direct sunlight, longer days. When it's tilted away, it's winter, less direct sunlight, shorter days. 6 months later, the situation reverses. The southern hemisphere gets its turn for summer. This tilt came from the same collisions that formed Earth. A glancing blow early in its history knocked Earth's axis off vertical, and it's been tilted ever since. Mars has a similar tilt, about 25 degrees, almost the same as Earth. So Mars has seasons too: summer, winter, spring, fall. But Martian seasons last longer because a Martian year is almost twice as long as an Earth year. Venus, on the other hand, has almost no tilt, just 3 degrees. So Venus has no seasons. The sun is almost always directly over the equator. Uranus, as we mentioned, has 98 degrees. It's spinning on its side. So Uranus has extreme seasons. Each pole faces the sun for 42 years straight, then darkness for 42 years. Imagine living on Uranus. Summer would mean constant daylight for decades. Winter would be decades of night. Axial tilt is random. It depends on the planet's history, the collisions it endured. But once established, it's stable, long-lasting. Earth's tilt has been roughly the same for billions of years. It wobbles slightly, a motion called precession. Over 26,000 years, the axis traces out a circle, but the tilt itself remains about 23.5 degrees. And that tilt, combined with Earth's orbit, gives us the rhythm of seasons: spring, summer, fall, winter. A cycle that has repeated for as long as life has existed on Earth, and will continue as long as Earth continues spinning, which is to say, forever.
The stability of orbits. Why planets don't crash. Here's a question you might be wondering. With all these planets orbiting, spinning, pulling on each other, why doesn't the solar system collapse? Why don't planets crash into each other or spiral into the sun? The answer: orbital mechanics and the laws of physics. Orbits are stable, remarkably stable. Once a planet is in an orbit, it tends to stay in that orbit unless something dramatic happens. The reason is conservation of angular momentum. A planet orbiting the sun has a certain amount of angular momentum, and that momentum is conserved. For the planet to spiral into the sun, it would have to lose angular momentum, but there's nothing to take it away. Space is a vacuum, no friction, no drag.
For a planet to escape the solar system, it would need to gain energy, but there's nothing to give it that energy. So, planets stay in their orbits, stable, predictable. There are perturbations. Gravitational interactions between planets cause slight wobbles, slight changes. Jupiter, being so massive, pulls on everything. It nudges orbits, slightly. Over millions of years, these perturbations add up. Orbits shift very slowly. But the changes are gradual, gentle. The solar system is stable on human timescales and even on geological timescales. Computer simulations show that the orbits of the inner planets, Mercury, Venus, Earth, Mars, will remain stable for billions of years. There's a tiny chance, less than 1%, that Mercury's orbit could become unstable in the next 5 billion years. It could crash into Venus or into the Sun, but it's unlikely. For the most part, the solar system is a well-oiled machine. Planets orbiting, moons circling, everything in motion, everything in balance. A cosmic clockwork running smoothly for billions of years. And it will continue, because once set in motion, orbits endure. Graceful, patient, eternal.
The Milky Way's slow spin, our galactic carousel. Right now, you're on a galactic carousel. The Milky Way, our home galaxy, is spinning, rotating around its center, and you're moving with it. The entire solar system, Sun, Earth, all the planets, is orbiting the galactic center at about 228,000 kilometers per hour. That's over 230 kilometers per second, faster than anything humans have ever built. And yet, you don't feel it, because everything around you is moving at the same speed. The nearest stars, the gas clouds, the dust, all of it rotating together. But how long does it take to complete one orbit? About 225 to 250 million years. Astronomers call this a galactic year or a cosmic year. Think about that. The last time our solar system was at this exact point in the galaxy's rotation, dinosaurs didn't exist yet. The supercontinent Pangaea hadn't formed. Life on Earth was still mostly in the oceans. That's how slowly the galaxy spins. From our perspective, the stars seem fixed. Constellations remain the same throughout a human lifetime. But they're not fixed. They're all moving, orbiting at slightly different speeds, slightly different distances from the galactic center. Over tens of thousands of years, the constellations slowly change, drift apart, form new patterns. But it's so gradual, so patient, that we never notice in our brief lifetimes. The Milky Way has been spinning since it formed, over 13 billion years ago. In its entire lifetime, it has completed only about 50 to 60 rotations, 50 or 60 spins in 13 billion years. That's patience on a cosmic scale. And it will keep spinning for billions of years more, until it merges with Andromeda, until the two galaxies become one. And even then, the new galaxy will spin, because angular momentum is conserved. The Milky Way spins because the gas cloud that formed it was spinning, because countless stars, collapsing from that cloud, each brought their own angular momentum, and because nothing in space can stop it. No friction, no resistance, just eternal, graceful rotation. You are moving through space at 230 kilometers per second, right now, as you rest, carried by a galaxy that has been spinning since before Earth existed, and will continue spinning long after Earth is gone. Why galaxies have spiral arms? Waves of star formation. If you've seen pictures of spiral galaxies, you know they're beautiful. graceful spiral arms curving outward from a bright central bulge. Our Milky Way is a spiral galaxy. So is Andromeda and billions of others. But here's a question. If galaxies are spinning, why don't the spiral arms wind up? Think about it. The galaxy rotates. Stars near the center orbit faster than stars farther out. So over billions of years, shouldn't the spiral arms wind tighter and tighter until they're completely twisted up? But they don't. Spiral galaxies millions of years old still have graceful open spiral arms. Why? The answer is elegant. The spiral arms aren't made of the same stars all the time. The arms aren't solid structures, they're density waves. Think of a traffic jam on a highway. Cars slow down as they pass through the congestion, then speed up again once they're passed. The traffic jam, the area of congestion, stays in one place, but the cars within it are constantly changing. Spiral arms work the same way. They're regions where stars, gas, and dust are more densely packed. Stars pass through the spiral arms as they orbit. They slow down slightly, spend some time in the arm, then speed up again once they've passed through. The arms themselves stay roughly in place, rotating, yes, but more slowly than the stars. So the spiral pattern is stable, enduring, and within those arms something wonderful happens. The density causes gas clouds to compress, and compressed gas forms stars. So spiral arms are where most star formation occurs. Young, hot blue stars light up the arms, making them bright and visible. These young stars are short-lived. They burn out before they drift away from the arm. So spiral arms always appear bright, full of young stars, while the space between the arms is darker, filled with older, dimmer stars. The Milky Way has several major spiral arms: the Sagittarius arm, the Perseus arm, the Norma arm. Our solar system sits near the inner edge of the Orion arm, a smaller spur between two major arms. We're moving through this arm, slowly. Over millions of years, we'll drift to another part of the galaxy, but the arms will remain. Density waves, guiding star formation, shaping the galaxy's appearance. Spiral galaxies are living, dynamic structures, not solid, not static, but fluid, ever-changing. And yet their spiral pattern endures for billions of years, a testament to the elegance of gravitational physics and to the universe's love of motion.
When galaxies collide, a dance of destruction and creation. Galaxies don't stay isolated forever. Gravity pulls them together, and sometimes they collide. But collide is a misleading word because galaxies are mostly empty space. Stars are so far apart that when two galaxies merge, individual stars almost never actually hit each other. Imagine two swarms of fireflies drifting through each other on a summer night. The fireflies don't collide, they simply intermingle. That's what happens when galaxies merge. The stars pass by each other, harmlessly, but gravitationally it's chaos. The two galaxies' gravity fields interact, pull, distort. Stars are flung into new orbits. Some are ejected entirely, shot out into intergalactic space. Long tails of stars stream out, tidal tails, bridges of stars connecting the two galaxies as they merge. Gas clouds collide, and when gas collides, it compresses, heats up, forms stars. Galactic collisions trigger intense bursts of star formation, starburst galaxies glowing brilliantly with newly born stars. Over hundreds of millions of years, the two galaxies spiral around each other, gradually merging. Their supermassive black holes at their centers also merge, creating an even more massive black hole. And eventually, the two become one. A single, larger galaxy, usually elliptical, smooth, featureless, lacking the spiral structure of its parent galaxies. Our Milky Way is on a collision course with Andromeda. In about 4.5 billion years, the two will begin to merge.
From Earth, if Earth still exists, the night sky will change dramatically. Andromeda will loom larger and larger, eventually filling the sky. Stars will be flung about. The sun might be cast into a different part of the galaxy or ejected entirely. But life on Earth, probably fine. The chances of any star actually hitting another star are astronomically small. The changes will be gradual, over millions of years, and eventually the merger will complete. The two galaxies will become one, a new galaxy, sometimes called Milkomeda or Milkdromeda, and it will spin, a combination of the Milky Way's spin and Andromeda's spin, because angular momentum is conserved. The dance continues, just with new partners in a new configuration. Galactic collisions are happening all over the universe right now. We've photographed many of them, galaxies in various stages of merger, some just beginning to touch, spiral arms reaching out, others deep in the process, distorted, stretched, streams of stars connecting them, and some finished, smooth elliptical galaxies, settled, calm, as if nothing dramatic ever happened. But it did. Two galaxies collided, merged, became one, and through it all, the motion never stopped, just transformed, redirected, continued. Dark matter, the invisible hand shaping galactic spin. Here's a puzzle that troubled astronomers for decades. When they measured how fast stars orbit in galaxies, something didn't add up. Stars far from the galactic center were moving too fast. According to Newton's laws, stars farther out should orbit more slowly, just like planets in our solar system. Neptune orbits much more slowly than Earth, but in galaxies, stars far from the center orbit at about the same speed as stars closer in. That shouldn't be possible unless there's more mass than we can see, much more. Galaxies, it turns out, are surrounded by halos of invisible matter, dark matter. We can't see it. It doesn't emit light, doesn't interact with light, but we can detect it through its gravity. It pulls on stars, on gas, on entire galaxies, and there's a lot of it. For every kilogram of normal matter, stars, planets, gas, there's about 5 kilograms of dark matter. Galaxies are mostly dark matter. The stars we see are just a small fraction of the total mass. And this dark matter is what holds galaxies together. Without it, galaxies would fly apart. The stars would escape. The spiral arms would dissolve. But dark matter provides the gravitational glue. It forms a halo around each galaxy, keeping everything in place, allowing the rotation to continue. We don't know what dark matter is. It's one of the biggest mysteries in physics. But we know it's there, and we know it's essential. Galaxies spin because of dark matter. The visible stars are just passengers, carried along by the dark matter's gravity. And that dark matter, it's in motion too, orbiting, swirling, dancing. We can't see it, but it's there, moving, always moving. Another reminder that the universe is full of motion, even in the invisible parts. Even in the things we can't detect, the dance continues. At the center of most galaxies, including our Milky Way, sits a supermassive black hole. These aren't like stellar black holes formed from dying stars. These are millions, even billions times more massive than the Sun. Our galaxy's black hole, Sagittarius A*, has a mass of about 4 million suns. Andromeda's black hole, over 100 million suns. And these black holes are spinning fast. Black holes can spin just like planets, stars, and galaxies. But black holes are different because they're so extreme. A spinning black hole drags space-time itself around with it, a phenomenon called frame dragging. Near the event horizon, space-time is swirling, like water going down a drain. Anything near the black hole, gas, dust, or even light, is dragged along by this swirl. We can measure black holes' spin by watching how matter orbits around it. And we found that most supermassive black holes are spinning, some at nearly the speed of light. Why are they spinning? For the same reason everything else is.
They formed from spinning material, gas clouds collapsing into the center of galaxies. And as they accreted more matter, they spun faster. When two galaxies merge, their black holes merge too, and the resulting black hole combines their spins. Angular momentum conserved, even in the most extreme objects in the universe. These black holes don't just sit there, they shape their galaxies. Jets of particles shoot out from near the black hole, traveling at nearly the speed of light, spanning thousands of light years. These jets heat surrounding gas, prevent it from cooling and forming stars. In a way, the black hole regulates star formation in the galaxy. A spinning black hole, millions, even billions times more massive than the sun, dragging spacetime, shaping a galaxy. All of it in motion, all of it dancing. Even the darkest, most extreme objects in the universe can't escape the cosmic rule. Nothing stands still.
Now let's zoom out, all the way out, to the largest scale, the structure of the universe itself. Galaxies aren't scattered randomly through space. They cluster, thousands of galaxies bound together by gravity, forming galaxy clusters. And those clusters are connected by filaments, long thread-like structures made of dark matter, gas, and galaxies. And between the filaments, voids, huge, empty regions where almost nothing exists. Together, this forms the cosmic web. It looks organic, like neurons in a brain, or like a sponge, threads of matter surrounding empty bubbles. And the web is in motion. Galaxies drift along the filaments, pulled by gravity. Clusters merge, filaments grow, voids expand. Everything is moving at the grandest scale imaginable. Our Milky Way sits in a filament, part of a structure called the Laniakea supercluster, which contains about 100,000 galaxies. And Laniakea itself is moving, drifting toward an even larger concentration of mass called the Shapley supercluster. We're all flowing like rivers of galaxies, pulled by invisible currents of dark matter. The universe is not static, not frozen. Even at scales of hundreds of millions of light years, motion persists. Slow, patient, but real. Computer simulations show how the cosmic web formed, how tiny fluctuations in the early universe, quantum ripples, grew over billions of years. Gravity amplified those ripples. Dense regions became denser, attracted more matter. Sparse regions became emptier. Matter flowed away. And over time, the web emerged, a network of filaments and voids, all of it in motion, all of it flowing. The universe is a river, and we're part of the current, carried along by forces we can barely comprehend, but carried nonetheless, moving, always moving. Newton's first law, the universe's most stubborn rule. Let's start with Isaac Newton. Over 300 years ago, he wrote down 3 laws of motion, simple statements that describe how objects move. The first law is the most fundamental. An object in motion stays in motion. An object at rest stays at rest, unless acted upon by an external force. This is called the law of inertia, and it's the reason nothing in space ever stops. Think about it. If you're floating in empty space and you push off from something, you'll drift forever. You won't slow down, you won't stop, because there's nothing to stop you. No friction, no air resistance, no force acting against you. You'll just keep moving at the same speed, in the same direction, eternally. This is why the planets keep orbiting, why galaxies keep spinning, why particles keep moving. Once motion begins, it continues, unless something actively stops it. And in the vacuum of space, there's nothing to provide that stopping force. On Earth, things seem to naturally stop. Roll a ball, and it eventually comes to rest. But that's not because of some inherent property of motion. It's because of friction. The ball rubs against the ground. Air resistance slows it. Energy is lost to heat. Remove friction and the ball would roll forever. In space, there is no friction, no air, no ground. So once something starts moving, it never stops. The Earth has been spinning for 4.6 billion years, not because it's constantly being pushed, but because nothing is stopping it. Newton's first law is stubborn, relentless. It says the default state is continuation. Motion persists. Stopping requires intervention, and in space, that intervention rarely comes. So the universe moves forever, not because motion is being added, but because it was there from the beginning and nothing has taken it away. This is the foundation of everything we've discussed. The Big Bang set things in motion, and Newton's first law ensures they stay in motion for billions of years, for eternity, unless something dramatic happens.
Why absolute zero doesn't mean absolute stillness. Let's talk about temperature again. We discussed earlier that temperature is just atomic motion. The faster atoms move, the hotter something is. So logically, if you could cool something down to absolute zero, the coldest possible temperature, atoms would stop moving, right? Wrong. Even at absolute zero, atoms still move. It's called zero-point energy, and it's a consequence of quantum mechanics. Remember the Heisenberg uncertainty principle? You can't know both position and momentum exactly. If an atom were completely still, its momentum would be zero, exact, which means its position would be completely uncertain. It could be anywhere. That's not possible. So even at absolute zero, atoms retain some motion, some kinetic energy. They vibrate, jitter, move. Not much, the minimum amount allowed by quantum physics, but it's not zero. Absolute stillness is forbidden by the laws of quantum mechanics. We've never achieved absolute zero in a laboratory, and we never will, because it's impossible, not just practically, fundamentally. The third law of thermodynamics says you can approach absolute zero, get closer and closer, but you can never reach it. And even if you could, atoms would still move, because motion is built into the fabric of quantum reality. Particles must have zero-point motion. It's not optional. So even in the coldest, most isolated place in the universe, motion persists. At the quantum level, nothing is ever truly still, not even frozen solid, not even at temperatures approaching absolute zero. Motion is fundamental, unavoidable, eternal. Entropy, the universe's one-way arrow. Let's talk about entropy. Entropy is a measure of disorder, randomness. And the second law of thermodynamics says, in a closed system, entropy always increases. Things naturally become more disordered, more spread out, more random. A dropped glass shatters. It doesn't spontaneously reassemble. Heat flows from hot objects to cold, not the reverse. The universe is moving toward maximum entropy, maximum disorder. This is called the heat death of the universe. A state where everything is evenly distributed, no temperature differences, no energy gradients, nothing left to happen. But here's the thing, entropy and motion are connected. Higher entropy means more randomness, more spread out energy, and energy in a high entropy state is still moving, just randomly. In a gas, molecules zip around in all directions, chaotically, high entropy. In a solid, molecules are organized, structured, low entropy. But in both cases, molecules are moving. The difference is the type of motion, ordered versus disordered. As the universe ages and entropy increases, motion doesn't stop, it just becomes more random, more chaotic, more evenly distributed. Right now, the universe has structure, galaxies, stars, planets. These are low entropy pockets, organized matter, but they're temporary. Over trillions of years, they'll disperse. Stars will burn out, black holes will evaporate, matter will spread thin. Eventually, the universe will be a cold, dark, empty expanse, high entropy. But even then, motion will persist. Particles, whatever's left, will still be moving, drifting, vibrating, just very slowly, very randomly. Entropy doesn't end motion. It just changes its character, from organized to chaotic, from structured to random. But motion itself, eternal, Because the universe at its core is dynamic, not static. And dynamics means motion, forever. Why stopping would break the universe? Here's a thought experiment. Imagine you could stop completely. Not just relative to Earth, but absolute stillness relative to the entire universe. What would happen? First, you'd violate conservation of momentum. Your momentum would have to disappear, go somewhere. But where? There's nowhere for it to go. Second, you'd violate quantum mechanics. Your position and momentum would both be exact. Zero momentum, precise location. Heisenberg says, impossible. Third, you'd have zero kinetic energy, zero temperature. But we just learned, even at absolute zero, particles move. So you'd be colder than absolute zero, which is impossible. Fourth, you'd be outside space-time's flow, because space-time itself is dynamic. It's expanding, rippling, moving. To be truly still, you'd have to exist outside space-time, outside reality. Fifth, you'd break causality. In relativity, there's no absolute now. Time is relative. Different observers experience different sequences of events. If you were absolutely still, you'd define a universal now, a privileged reference frame. But relativity says there is no privileged frame. All motion is relative. So absolute stillness would contradict the structure of space-time itself. In short, true stillness would break physics. Multiple fundamental laws would have to be violated. The universe would have to reorganize itself, change its rules. That's why stillness is impossible. Not just impractical, not just unlikely, fundamentally impossible. The universe's laws forbid it. Motion is woven into the fabric of existence at every level in every law. And nothing can escape it. Take a deep breath. Let it out slowly. In this chapter, we've explored the deepest reasons why nothing can stand still. Newton's first law says motion persists unless stopped, and in space, nothing stops it. Conservation of momentum says motion can't be destroyed, only transferred. The vacuum of space removes friction, the enemy of motion. Even at absolute zero, quantum mechanics requires motion. Entropy doesn't end a motion, it just makes it more random. Space-time itself is dynamic, rippling, moving. And absolute stillness would violate multiple fundamental laws, break physics itself. Motion is not an accident, it's the nature of reality. The universe is not a collection of static objects, it's a process, a dance. Everything moves, always has, always will. And you're a part of that. Not separate from it, not observing from outside. You are motion. Your atoms, your molecules, your body, your planet, your galaxy, all of it moving, all of it dancing. And that's not something to fear, it's something to embrace. Because motion is life, motion is existence. To be is to move. In the final chapter, we'll bring it all together. We'll reflect on what this means for us, for the universe, for the eternal dance that never ends. But for now, rest. Let these truths settle. You are motion, and motion is eternal. Good night. See you in the final chapter.